Hello and welcome back. Today we're going to be talking about the Z80 processor architecture and get started wiring it up on the breadboard. The Z80 was introduced by Zilog in July of 1976. It was designed by Federico Fajan, who designed the Intel 4004, 8008, and the 8080 microprocessors. It has 8 data pins and 16 address pins, so it can address 64K of memory, 0 through 65535. It supports input and output through the use of an 8-bit I/O addressing system, meaning it could support 256 input or output channels. It was actually designed for embedded systems like cash registers and industrial robots, but it became one of the most widely used CPUs in computers in the late 70s, early 80s. Because of its ease of use and popularity, it's still being produced today, although they've increased the speed of the processor. It'll now run from 6 MHz up to 20 MHz. Having it ready, available, and at a low cost is a great benefit for this project. Another benefit of using this processor for our project is it has no lower boundary on the speed. We can set up a button for the clock and manually step through the instructions, which is great for debugging. So to get into the architecture of the Z80, take a look at this block diagram of it. This shows the major components of the CPU and its connections to the outside world. Up here we have the data bus interface, which connects the system 8-bit data bus to the internal CPU data bus. The internal data bus connects all of the major subsystems within the CPU, including the arithmetic logic unit, or the ALU, the instruction register, where the instructions are stored during the M1 cycle, and the register array that contains all of the internal registers. We'll get into more detail on these in just a minute. Down here we have the system's 16-bit address bus that connects to the internal address buffers. Over here we have the 8 system and CPU control outputs and the 5 CPU control inputs. These interface to the CPU timing control logic. Again, we'll get to these in just a minute. So during the instruction cycle, the opcode is read from the data bus and placed into the instruction register. The instruction decoder then works with the other subsystems to execute the command. But right now I want to go into more detail on the register array and what registers this contains. The Z80 has 208 bits of read-write registers that can be used in programming. The accumulator is an 8-bit register that holds the results of 8-bit arithmetic operations. The flag register indicates specific conditions for an 8 or 16-bit operation, such as zero condition, among others. There are also 3 other 16-bit registers that can be used as needed: BC, DE, and HL. They can also be addressed as 8-bit registers as B, C, D, E, H, or L. Now each of these 4 registers has a complementary set. They are indicated by the tick marks at the end of the letter. These register sets can be swapped out with one command. Now the importance of these registers is apparent when creating embedded ROM-only systems. This gives you the ability to temporarily store values without having to push to the stack, which requires external RAM. There are also a few special purpose registers such as the program counter and stack pointer. The program counter holds the 16-bit address of the current instruction in memory, and it's incremented as we move through the instructions. The stack pointer is a 16-bit register that points to the current bottom of the stack in RAM. The stack is a temporary external RAM location where values can be placed with the push command and then pulled back with the pop command at a later time in a last in, first out order. For example, on a call command, the current address in the program counter is pushed to the stack. The call is made, and as long as the routine popped the same number of bytes it pushed, the return address will be the next 2 bytes on the stack. And when the return command is encountered, the CPU pops the address back into the program counter, increments it, making the command after the call the current command. We'll talk about this more later. We also have 2 16-bit index registers, IX and IY. They hold a base address that can be used in indexing addressing modes. This enables us to use tables of data that can easily be addressed. There's an interrupt page address register, I. This is used for mode 2 interrupts. You load the high 8 bits of the interrupt address into I, and then the interrupting device provides the lower 8 bits. We'll get into more of this later when we discuss implementing interrupts. There's also a memory refresh register, but since we aren't using dynamic memory, we won't need to use this. Alright, let's take a look at the pinout of the CPU. As you can see here, the Z80 uses a 40-pin interface. Now this chart here is a logical layout and does not reflect how the pins are arranged on the chip. But over here on the right side you can see the 16-bit address bus and the 8-bit data bus. On the left side you can see the system control pins, the CPU control pins, the bus control pins. And also you have the clock input and the power and the ground. Now up here in the CPU control section, it contains 1 output and 4 input pins used to control CPU activity. The halt pin is an output that goes low when the CPU encounters a halt command. The CPU then continues to process NoOp or no operation instructions until there's a reset or an interrupt. Here you can see the wait pin. This is an input that allows other components of the system to tell the CPU to wait while a process is finishing. For example, if there was slow RAM in the system, the wait could go low until the memory process was complete. The interrupt and the non-maskable interrupt pins tell the CPU that another part of the system needs to execute code to handle an event. This event could be something like a key press on a keyboard, an input signal from an external port. We'll get into this in depth as we start adding more components to the system. The reset pin clears the registers, resets the stack pointer and the program counter, and then basically resetting the computer. Now looking up here at the system control pins, you see that they're all outputs from the CPU. These are used to generate the logic to enable other components in the system. M1 indicates that the processor is in the first cycle of the instruction cycle. Since this cycle accesses memory, the M1 pin is used to ensure that only the CPU has access to the data bus at that time. MREC, or memory request, is used to indicate that the CPU wants to read or write data from memory. I/O request indicates that the CPU wants to read or write data from an I/O port. Read indicates that the CPU wants to read data from the data bus, and write indicates that the CPU wants to write data to the data bus. So for example, if MREC and read go low, it means the CPU wants to do a memory read at the address it has put on the address bus. The MREC and the RD lines would enable the memory chip output, latching the contents of the address onto the data bus. Notice that all of the system control pins are active low. Refresh is only used with dynamic RAM, which I'm not using, so I'm going to ignore that for now. And I'm not going to talk about the bus control at this time either, as it isn't used in the system yet, but I will address it in the future. Let's talk a bit about how the Z80 accesses memory and I/O ports. When the processor wants to access memory for reading, it puts the memory address on the address bus, and then the MREC and the read pins drop low. The memory module uses logic chips to enable the chip enable and the read pins on the memory chip. This connects the memory output to the data bus, where the CPU can read it. When it wants to write data, it puts the address on the address bus and the value on the data bus, and then it pulls the MREC and the read pins low. It's important to point out that during this time, the M1 pin should not be active. While the M1 pin is active, the processor is retrieving the command from memory. If we ignored that pin, we would wind up clashing on the bus. Now when the CPU needs to read from I/O, the I/O address is written to the lower half of the address bus, and the I/O request and the read pins are pulled low. Then the data can be placed on the bus for the CPU to read by the peripheral at the I/O port. At this time, the I/O device can activate the wait pin if it needs more time to get the data. And then once the data is placed on the bus, the CPU can read it. And when the CPU needs to write data to the I/O, the address is written to the lower half of the address bus, and the data is placed on the data bus, and the I/O request and the write pins are pulled low. As with the memory request, the device needs to make sure that the M1 pin is not low, as that is used with the interrupt process. Now let's explore how the Z80 processes instructions. Each instruction consists of a 1 or more byte opcode, possibly with register codes embedded, followed by 0 or more parameters. So for example, this instruction loads the value of one register into another register. The 1 byte opcode for this is encoded as follows. Bit 7 is a 0, bit 6 is a 1. Now bits 5, 4, and 3 contain a combination that indicate the 8-bit register to write to, and bits 2, 1, and 0 indicate the 8-bit register to read from. By using these 3-bit register codes, the entire command fits into 1 byte, meaning it can perform the command in fewer clock cycles. So the first step in this execution is to put the current address from the program counter onto the address bus. Then it does a memory read to have the memory put the opcode on the data bus. The CPU then reads it from the data bus and decodes the opcode. It then increments the program counter. If it can, it will then execute the command in the first step, as with the example of this command. This is referred to as the M1 step. Let's take a look at the timing charts for that first step. Each clock cycle is referred to as a T cycle. You can see the clock signal here. And on the rising edge of the clock in the T state 1, you can see that the contents of the program counter are placed on the address bus, and the M1 pin goes low, indicating that the CPU is in the M1 step. On the falling edge of the T1, MREC, which stands for memory request, goes active in the low state, as does the read. This causes the memory to put the contents of the memory address locations specified on the address bus onto the data bus. Everything stays the same on the rising edge of T2. However, if we needed more time to read from the memory or other component, that component could pull weight low and pause the CPU for 1 or more clock cycles. Now on the falling edge of T2, the wait ends, and the data bus is latched into the CPU instruction register. On the rising edge of T3, the MREC, the read, and the M1 go inactive, and refresh goes active. As I mentioned before, I won't spend any time on this since it's not used in the system. But also during T3 and T4, the opcode that was loaded into the instruction register is executed in parallel to the refresh. And that's the entire M1 cycle, and in this case, the entire command. On opcodes that use more than one machine cycle, the next T1 would perform the next step in the instruction. We will get more into detail on how this works as we start expanding the system, because these signals are going to be very important in adding more components to the CPU. So let's get to the breadboard and do some real-world scenarios. So this first circuit is going to be a push button with a 555 timer set up as a monostable multi-vibrator to allow me to step through the clock cycles so we can follow along with the timing diagrams. A monostable multi-vibrator is a circuit that is stable as one output, and that output can only change by action from another component, like a push button. I didn't show this in the last video because I'm only going to be using it while we're initially testing our circuits. Once you get into running programs from ROM, where commands can take 20 or more T cycles, pushing the button gets old very quickly. I'll put the 555 in here, and then I'll hook up power, and then ground. And keep in mind that ground on a 555 is pin 1, not pin 4 like it is on logic circuits. And pin 4 is a reset, which is active when low, so I'll tie that to 5 volts so it doesn't reset. And then I'll add my push button over here. Now pin 5 is a control pin, but we're not going to use it, so it's advised that we decouple it to ground through a small capacitor. So that's what I'm doing there. And then I'll connect pins 6 and 7. Add a resistor between pins 7 and 8, which is providing power to pin 7, and a capacitor to pin 6 and ground. Now I'll add a resistor between pin 2, the discharge pin, and 5 volts. This will pull the pin 2 high, and I'll also connect pin 2 to one leg of the push button, and the other leg, the other leg of the push button is going to be connected to ground, so that when it's pulled high through the resistor when the switch is open, but when I push the switch, it's going to short it to ground, pulling discharge low and setting the output to high. So let's also hook up an LED through a 1K current limiting resistor to ground. This will give us a visual indication of the clock value. I'm setting it up there in between the two pins of the push button, but it's not connected to it, just right there in the middle. And so with that, let's test it and see if we get blinky lights. Sure enough, there it is. And now if we look at it on the scope, you can see that when I push the button, I get a nice clean square wave, which is perfect for our clock. Each push of the button brings the clock high, and each time I let go of it, it drops straight back down to 0. There's no ramp up time or ramp up time. And I can also let the clock cycles go as long as I want to, just by holding or not holding the button. Okay, now let's add the Z80 CPU, and we'll want to add power and ground. Power is pin 11. It's right there. And ground is pin 29 over on the other side. You might notice I've got them marked on top of the chip there with a marker. And if you remember from earlier, we had several control pins that were active low, and we want to pull those high so we don't wind up resetting or waiting or interrupting. So here pin 24 is going to be the wait line. I'll tie that high. Down here on pin 16 is the interrupt line, and right next to it is the non-maskable interrupt line. Right there, yep. And then we've got the reset pin, which is 26, and I'll tie that high so that we don't just keep resetting in a loop and nothing happens. There we go. Okay, so let's go ahead and hook up the clock. But if you remember from our pin discussion, the clock is active low and our push button is active high. So we need to invert the clock signal. I'll use a 74 HCT14 Schmidt trigger inverter for that purpose. So let's get hooked up with power and ground, and power on pin 14 right there, and ground on pin 7 right there. And then I'll run our clock from pin 3 of the 555 into pin 1 of the HCT14. And then I'll run the output of that on pin 2 to the clock on the Z80, which is pin 6 right there. All right, now I want to hook up LEDs to the M1, the MEMREC, and the read pins. This will help us to see what's happening during each T state. Since they're active low, I want to run these through the inverter so the LEDs come on when they're active. So what I'm going to do is I'm going to connect the M1 pin, that's pin 27, to the first input on the other side of the inverter there, which would be pin 13. So I'm going from 13 to 27 over here, right? Yeah, 26, 27, yes. So that's where that's going. And then the read pin, which is pin 21, to the second input on this same side here. And get that in there. I'll throw it down here just so that it fits better. And then the MEMREC pin, which is pin 19, I want to put that to the third pin over here, which would be pin 9. So I'll stick that right in there and hook it up to 19. There we go. All right. So now what I'm going to do is I'm going to take the outputs of these over to this area where I don't have anything, so I can put the LEDs in there. And I'll do the M1 signal first, and then I'll do the read signal, and then the MEMREC signal. So let me get this here and put it, oh wait, that's the wrong one. Hold on one second. Yeah, that's the right one. So, nope, okay. Sorry about that. Having problems with my wire lengths. So I'll just set these in here like that. There we go. So there we go. Now I've got one every 3 holes for the LEDs. So I'll stick the LEDs in here, skip 2 and stick in the next one, and then skip 2 and stick in the last one. Now what I've got here is a resistor array, and basically it's just a group of resistors. The ground pin is right here, and the rest of the pins are 1K resistors all tied to that ground pin. It just saves a lot of space on the breadboard, makes it a little easier. So let me go ahead and stick that in here and get that plugged in. No, wait, hold on. I got to move it over one more hole. Otherwise I short out. There we go. Okay. And then I'll tie that ground pin to the ground. There, now we've got 3 resistors hooked up, ready to go. I'm going to label these just so I remember as we're going through it which one's which, because I've got a really bad memory. So yeah, that should help. Now all we have left is the address and the data pins, but without memory, how can we test our setup? Well, if we look here in the user manual, the no operation instruction does nothing. The CPU goes through its normal 4 T states, but it does not execute anything. Now the bytecode for the NoOp is 0. So basically it reads a 0, it goes to the 4 T states, it loads the next address into the program counter, and then it moves on. So if we tied our 8 data pins to ground, the CPU would read 0 as the first opcode and do nothing, but it still increments the program counter. So if we go back to the timing chart and see that in T1, the program counter is placed on the address bus. That means if we have the data pins tied low, the CPU will place a 0 in the address bus in T1 and read the data bus in T2, reading in that 0, do 3 and 4, and then perform no action and increment the program counter and start over. But this time the program counter contains a 1. This will effectively give us a 64K binary counter on the address bus. So we should be able to tie data low, hook up LEDs to the address bus, and see it counting in binary. So let's do that. Okay, so now we'll tie pins 15, 14, 13, and 12 to the ground. There we go. Okay, and then we'll skip 11, which is the power, and we'll do 10, 9, 8, and 7 to the ground, and that'll give us our 8 data pins all at a low value. Now if we were going to do anything else other than just test this NoOp, we couldn't tie these directly to ground, because if the CPU tried to write anything to the data bus, it would short straight to ground, and that would not be a good thing. We'd have to use some kind of pull down resistors. But for this application we can do this, but again, be careful with this. Okay, there we go. So we've got our 8 data lines pulled low, and I've got this board here that I just made. It's got a buffer on it and 8 LEDs with resistors, and I could just plug it into the address, which happen to be all consecutive pins, pin 30 through 37, and then we can look at the lower, oh, come on, get in there. There we go. Yep. Okay. No, come on. What's going on here? I think the wires are in the way. That's probably what it is. So there we go. Now I'll hook up the power and the ground, and if I plug this in, we should see some sort of activity, hopefully, no smoke. So let's plug her in and see what we got. Okay, here we go. Oh, we've got lights. Oh, I've got a loose solder joint. That's bad. All right, so let's push the button and see if anything happens. There we go. We've got an LED on MR. If I let go of the button, let's see what happens. Okay, that stays there. Oh, there we go. Now we've got the M1. So now we've got all 3, M1, MR, and read, still lit. And push it again, and they're still lit. Let go of it again, and they go out. And now we've got the MR. And if I let go, the MR should stay lit. And then when I push it back down, the MR goes out, and we've got our first light lit up here. So if I keep cycling through this, and we can watch the M1, the memrec, and there we go, we've got another one. So if I just keep going, we should be able to see the board counting in binary as we go through these steps of the T cycle. I mean the T cycles. So there we go, and now this should switch to, there we go, there's 4. And this one next should come up with 5. There we go. And so there we go. We've actually got a binary counter with a Z80 CPU. An incredible waste of this CPU for this application, but it works. So thanks for joining me. Please like and subscribe down below. In the next video, I'm going to match up the timing chart with our clock cycle steps, and then maybe get some memory hooked up to our CPU and see what kind of trouble we can get into. Don't forget to check out my website. I have schematics for these videos there, and also check out my Patreon page. The links are down below. Thanks very much. Have a great day.